I don't know how you dress for Thanksgiving. This might be a little bit over the top, but I know at my house we dress a different way. So I'm going to sort of get dressed the way I would when we have dinner at my house on Thanksgiving. And I'm sure you probably wear your lab coats too, don't you? Yeah, I figured you would. So let's start. We're really organizing this among or around this table. We're going to take a look at how a pop-up timer works. So in most of the turkeys that you buy in the grocery store, there's a little plastic pop-up timer. And I think we can actually switch to the camera and show you what it looks like. Maybe you'll recognize it once you see it. So these are a pop-up timer. The one on your left is what it looks like when it is inside the turkey. The one on the left is one that's been cut away. We really wanted to know how these worked. So Dr. Slagle, who's over here in the red sweater, and I one day spent a lot of time doing calculations on a napkin of gas laws to figure out what the pressure would have to be inside the pop-up timer in order to make it work. And then we decided, just for the fun of it, that we would cut it open after we had done all the kinetics and numerous calculations. And we found out that what it really is a spring, a plunger with a spring, and a small drop of solder. So let's switch to the PowerPoint, if we could. And you'll see on the right-hand side that there's a diagram of the actual plunger. So it's fully encased in plastic. The plunger is depressed. When the solder melts, the plunger is released. Now, the solder they've chosen just happens to melt at the same temperature that a turkey is considered done, which is 185 degrees Fahrenheit. So the pop-up timer cares nothing about your turkey. It really doesn't care at all. It really is obeying just the scientific principle of melting at a certain temperature. Once it melts, it releases the plunger and it comes up. Quite simple, quite elegant. It's really nice to see science in a simplistic form. So we're going to start with this question of why do we eat mashed potatoes instead of mashed paper towels? Now, is that a question that comes up at your dinner very often? Well, it comes up at my dinners, maybe because my mashed potatoes taste like mashed paper towels. If you guys get caught up, put it in your mouth, wad it down. Now, no spitballs. That's the first rule. There, see, I knew he was disappointed. We'll give you a few more seconds. I could sing a little bit, perhaps. All right, you can spit it out now if you'd like. Lovely, lovely. So let me ask you, your name is?
Billy.
Billy, when you first put it into your mouth and you first started chewing on it, how would you describe the flavor?
Pretty dull and papery.
Dull and papery, okay. Could you expand on that?
Didn't really taste like anything.
Didn't taste like anything. Do you have anything to add?
It's not very appetizing.
Not very appetizing. After you chewed it for a while, did the flavor change?
Yeah.
Did the flavor change at all?
Stronger.
Taste stronger, all right? Now we're going to move to potatoes. So we have a thin slice of potato here. So you're going to take this slice of potato, which came from my home, chew it up, and keep it wadded on your tongue. We want your saliva to actually do its thing. Aren't you so glad you volunteered? Isn't this great? I bet you haven't had this much fun all day. And what did the potato taste like in the beginning?
It tasted like starch, but then it turned it into dirt.
Starch into dirt, very good. But did the flavor change?
Yes.
It did change.
Yep.
What about you?
Dirt.
Dirt, in the beginning or the end?
The beginning.
In the beginning. And what did it taste like at the end?
Just a normal vegetable.
Normal vegetable. But did the flavor change?
Yeah.
Could you discern a change? What about you?
Yeah, I guess dirt tasting, and then it got very strong, kind of like acidic.
Strong and kind of acidic, okay? So here's what we've got. We said that potatoes and paper towels are similar chemically. They're both made up of carbohydrates. They both have long chains of glucose. So why do we care about glucose? Glucose is the energy that our body runs on. A lot of carbohydrates are actually converted into glucose through digestion. The difference between the paper and the potatoes is how the glucose units are joined together. So in the top part, you have the two glucose units, and connecting them is that red oxygen, which is actually an alpha linkage. So when you digest something, you actually have to have an enzyme that breaks that linkage. In cellulose, this is paper, we have a beta linkage. Notice that really the only thing that's different between the two is the shape of the linkage. It's made up of the same element, oxygen. It's only the shape. And enzymes in our body are really dependent upon shape. Let's advance to the next slide. So the reason the flavor changed on the potato but did not change on the paper towel is that when you are digesting potatoes, we do have enzymes that will break that alpha linkage. We don't have any enzymes that will break the beta linkage between glucose. So you can't digest paper. And the enzyme, the first enzyme that starts the digestion process is in your saliva. So you actually started breaking the linkage in the potatoes. That's why the flavor changed over time. The flavor that you had 2 minutes later was not the same as the initial flavor because amylase, which is the enzyme in your saliva, started to break that carbohydrate down into maltose. Maltose is not glucose. Maltose is two monosaccharides joined together instead of 20. Maltose eventually gets broken down into glucose, but that doesn't happen in your saliva. That happens through your digestive system. So yes, you could eat paper towels, but you wouldn't get any flavor out of them, and you wouldn't get any nutritive value out of them. But with potatoes, you will, even though chemically they're very similar, and it all has to do with enzymes. All right, so here are muffins. Really, really big muffins. What makes them rise? Have you ever thought about this? There's no yeast in them. Let's take a look at the recipe. You've got 2 cups of flour to make your normal muffin. You have 3 teaspoons of baking powder, 2 tablespoons of sugar, 1 egg, and a cup of milk. What do you think in there is actually responsible for the batter rising? The baking powder. But you know what? If you put baking powder in there alone, it wouldn't rise. You need two other ingredients and one other behavior. The other ingredient you have to have is milk. If you don't have milk or something that takes milk's place, you're not going to have a muffin that rises. The other thing that's very important about the recipe is that it says stir only enough to dampen the flour. And that means don't keep stirring. And don't leave it on your counter for a really long time because you're busy doing something else. So let's take a look at a demonstration here. We've got a Ziploc baggie. And in the Ziploc baggie, we have put a little bit of vinegar. The vinegar takes the place of the milk. Vinegar is an acid. Milk is also an acid. Milk contains lactose or lactic acid. So we've got something replacing the milk that was in the recipe. Now we're going to take a small piece of paper towel. Would you hold on to this avocado, please? Thank you. And let me make this a little bit smaller. We're going to put a tablespoon of baking powder into the paper towel. And I'm going to wrap up the paper towel and twist the ends. Now there are 2 ways to view what this looks like. Everybody has their opinion. I think of it as taffy. Of course, I did go to school in the 60s, so there is another explanation for what this looks like. The reason we do this is to slow down the reaction so that we can actually have time to close the bag. Now, here's something if you have younger brothers and sisters or you have nieces and nephews at Thanksgiving. This is a great experiment to do with them because it uses household ingredients. Have a Ziploc baggie, baking soda, paper towel, and vinegar. You're going to put this in here and then zip the bag shut. And with elementary school kids, we ask them if they can see something invisible. Elementary school kids will tell you can't see something invisible. That's the definition of invisible. Now, can you hear anything? You hear a chemical reaction. Can you see anything happening? What do you think is in there? Gas. Anybody know what the gas is? CO2. Let's take a look at this chemical reaction here. The baking soda is sodium bicarbonate, the bi meaning hydrogen. So you have NaHCO3 plus any acid. In this case, we're representing acid as HA, H being the important part of the acid. You're going to have a chemical reaction, a double replacement reaction, where the sodium bicarbonate breaks between the sodium ion and the bicarbonate ion, and the acid breaks between the hydrogen ion and whatever the negative part of the acid would be. And they change partners. So you're going to have H from the acid going with the HCO3 forming carbonic acid, H2CO3. And then what's left over is the sodium and whatever the other part of the acid is. The sodium and the other part of the acid is dissolved in the liquid at the bottom. Carbonic acid is unstable. So if you look at the second reaction, as soon as carbonic acid is formed, it immediately breaks apart into CO2 and water. The water mixes with the vinegar that's down here, and the CO2 is what you feel in the bag. Now, if you put in too much vinegar or too much baking soda, and you're doing this with young children, the bag can actually get so full of CO2 that you have to burp it. The way you burp it is just by opening up opening the bag a little bit, letting some of the CO2 out so it doesn't rip the seams of the bag. So how does this relate to muffins? You put the baking soda and you put milk into muffins. The same reaction occurs with CO2 being produced. If you stir it too much, the CO2 is going to come out of the batter before you put the muffin in the oven. If you leave it on your counter, the CO2 that's produced is going to seep out of the batter, and by the time you put it into the oven, there'll be no CO2 left in the batter. So now you put the batter in the oven, the CO2 comes out of the batter, and heat increases the rate by which it leaves the batter. As the CO2 comes up out of the batter, it pulls the batter up with it. And since the oven is hot, the batter bakes in the up position. By the time you eat the muffin, the CO2 has gone, but the batter has baked in the up position. If you beat it too much, there won't be enough CO2 to make your muffin rise. If you leave it on the counter, there won't be enough CO2 to let your muffin rise. So that's why the directions always say, beat it just until the ingredients are moistened. All right, let's go to the next one. All right, that bloated feeling. You know when you have finished with your Thanksgiving dinner and you just feel really, really full. We want to give you an idea of what that's like and what's causing that. So I need a very strong volunteer. Here are your goggles. Your name is?
Chris.
Chris. All right, Chris. This is a baby bottle. Many of you have young nieces, nephews, brothers, and sisters at home, maybe even children at home. And we order these nipples from Evenflow, the company that makes them, and we order them before the hole is put into the nipple. So there is no hole in this nipple. So I'm going to ask you if you would blow this up, just like you would a balloon.
Okay.
Keep going. Blow harder. Oh, yeah, I'm sure it will. Keep going. Give it one last try. Well, you can't blame them for trying. Well, thanks, Chris. I appreciate your effort. What we're going to do here is take some ginger ale. Would you open that can for me?
Oh, of course.
Thank you. You can even take a sip if you'd like. We're going to fill the baby bottle about 3/4 of the way with this ginger ale. And by the way, if you ever do this demonstration, be sure that you use a colorless soda in case it doesn't work. And we're going to squeeze, or we're going to twist this on. Now what I'd like you to do is to shake this up and down, forcing the CO2 out of the soda. Don't keep your finger on the top, though. Actually, even though he couldn't blow it up, the CO2 that is released from the soda will actually cause this, which is fairly thick plastic, to inflate. This is what's happening inside your intestines. So when you have bloated feeling and you've been drinking a lot of soda, this is why. Interesting, isn't it? Thank you, Chris. I appreciate your help.
You're welcome. Is that it? Or?
Yeah, I think that'll do it. Thank you. So the reason that you should use colorless soda is that if you forget to put the top on really tightly, the soda is going to come all out all over you. So you don't want to do it with Coke or anything like that. And if you do this demonstration several times with the same nipple, it will eventually burst. So now we have a hole in it. All right. Also use cold soda. Why would you use cold soda? Because there'd be more CO2 dissolved in it. That's right. CO2 dissolves to a greater extent in a cold liquid than a warm liquid. So if you used room temperature soda, you wouldn't have as much CO2 coming out of it when you shook it. Let's move along. When you've been eating dinner for a long time, if you overeat, you sometimes get an upset stomach. And when you get an upset stomach at Thanksgiving, what do you normally do besides throw up? Take Pepto-Bismol or some type of antacid. So here's why you do an antacid. Your stomach normally produces acid to digest the food. That's actually how we digest food. The stomach secretes acid, and that's what starts some of the digestion in the stomach. If you take in a lot of food, your body's going to overproduce that acid. If your stomach is very full of food, some of that acid could actually go back up the esophagus, and that's that heartburn that you sometimes feel. So when you are uncomfortable this way, one of the things you might want to do is to take an antacid. Now, what do you think an antacid really is? It's a base. So you're actually causing a neutralization reaction between the excess acid that's in your body and this base that you're ingesting. So we have 3 Erlenmeyer flasks here, which we're going to put near the camera. And in it, we're going to simulate the acid that's in your stomach by putting 10% hydrochloric acid into the Erlenmeyer flasks. We're going to put in probably about half an inch worth on the bottom. So Princess Avogadro will put some acid in. And then what we're going to do is we're going to test 3 antacids: Alka-Seltzer, Tums, and then an old-fashioned remedy for upset stomach, which is baking soda. Do we have baking soda out? So before antacids were commercially available, the thing that you used to do would be to take a teaspoonful of baking soda and a glass of water, and that would do it. So we've actually crushed the tablets of Alka-Seltzer in here, and we've crushed an equivalent amount of Tums, and then we've taken the teaspoonful of antacid, and we have filled 3 balloons with them. So we have, let's go through the colors on this. What color, what's in?
This is Tums.
Tums is in the orange. So we're going to put that balloon over the top. You might need to help her hold on to it. We're not going to release the antacid into the acid until we're ready and we have all 3 of them set up. One person hold the Erlenmeyer, I think, and one person hold the balloon. And the crushed antacid is actually in the bottom of the balloon. So when we are ready, we'll pull the balloon up and release all of the antacid into the acid at the same time. Now, when you have a neutralization reaction, the hydrogen ion from the acid and the hydroxide from the base will actually form water, and then you'll have some other salt. In this case, we may also have another byproduct. So let me get this straight. Orange was what?
Tums.
Tums. So I'm going to line, let's move this. Let's move it here. So Tums is over here on the orange, and the yellow is?
So baking soda?
Baking soda. And the blue is Alka-Seltzer. All right, so I'm going to get behind this container or this table, and we're each going to take one of these and we're going to release them on the count of 3. You ready? 1, 2, 3. This is the same reaction that goes on in your stomach. And you'll notice that a gas is being generated. Which one is generating the most gas? Baking soda. What do you think that gas is? It's not oxygen. Baking soda is sodium bicarbonate, remember? NaHCO3. What do you think it is for the baking soda? CO2. And if you look at the ingredients of Alka-Seltzer lists its ingredients as citric acid and sodium bicarbonate. So it actually has the same ingredient as the old-fashioned method, but not as much. You can see that you're not producing as much CO2. And then Tums uses calcium sulfate instead of sodium bicarbonate, and that reaction is less and slower. If this is happening in your stomach, now your stomach is up here. It's not down here, it's up here. If this reaction is happening in your stomach and that CO2 is produced, that CO2 has to go someplace. If you have taken your antacid and then you start to talk, that CO2 is going to come out of your esophagus and it's going to come out as a burp. So burping is actually your body's releasing of that CO2 that has been generated in your stomach. So I think we will burp these three and release the CO2. We won't get the same noise here that you might get at home. This is a chemistry lab anyway. Just be careful because there is acid in there. And that pretty much will take care of the excess acid that's in your body. Let's go back to the PowerPoint. So the balloon contains the CO2 that's generated as the byproduct. The CO2 generated this quickly in the stomach will actually be released as a burp. If it happened in your intestines instead of your stomach, the CO2 would come out the other end. But it happens in your stomach, thank heavens. Well, that pretty much sums up Thanksgiving dinner, from everything that's on the table to how you feel afterwards to cleaning up. So we'd really like to thank all the people that had a lot to do with making this presentation possible. The Office of Campus Activities, the Department of Chemistry, graduate students, undergraduates, chemistry staff, the Martin Maloney Society, the Center for Planning and Information Technology, otherwise known as CPIT, the American Chemical Society Membership Division, Office of Public Affairs and Education Division for sending us all the freebies. And we want you to have a really happy Thanksgiving and share some chemistry with your family and friends. Thank you for coming. Not bad for time.